Hello, this is Team 2, and our team members are Tonga Kang and Ozan Güneş, and I'm in Sunbaek. This is our final presentation of improvements on Eagle 3D multi-object tracking via sensor fusion. For a safe robot navigation and motion planning, mobile agents need to be aware of surrounding objects and foresee their future states. For that, many researches have done on multi-object tracking for safe navigation and motion planning. The researchers have done researches on 2D MOT and 3D MOT. For 2D MOT, research is focused on tracking objects in image space using camera, for example, Kalman filter, optical flow, etc. 2D MOT has a low computational complexity, which leverages a rich visual signal. Therefore, it can localize objects in occlusions and all the ones too far away. However, since it lacks depth information, it struggles to accurately tracking objects in crowds or real-world 3D scenarios. There are also researches done on 3D MOT. 3D MOT utilizes depth data from sensors like LiDAR or stereo cameras, allowing more sensitive to reflective and low albedo surfaces. However, it has limited sensing range due to input signal sparsity. For such limitations of 2D and 3D, there have been various previous fusion-based methods. One of them are a stereo vision-based approach, which maintains each track's position jointly in both 3D and image domains, updating them with partial object evidence. Another is Beyond Pixels, which uses monocular SLAM for 3D localization, providing an alternative method for integrating visual data. Lastly, Mode Fusion, which combines various data sources, optical flow, scene flow, stereo depth, and 2D detections to track objects in 3D space, showcasing a comprehensive approach to tracking. The paper we are focusing on is Eagle Mode. Eagle Mode makes difference from previous method. Firstly, by Eagle Mode treats different sensors modality independently. Second, Eagle Mode relies only on bounding box object detections obtained from two complementary sensor modalities and scales well across different sensory environments. That is single LiDAR and multiple cameras. So Eagle Mode integrates the 2D motion and location information with 3D geometric informations, and it associates detections across frames in both 2D and 3D spaces, enabling better handling of occlusions and spatial interactions. We mainly focused on two things in this project. First is a replication, and second is improvement. Let's see what we have done in replication. We ran Eagle Mode on personal desktop equipped with a single GPU, and also we conducted experiment with the Kitty dataset and visualized 2D and tracking results. Let's see what we have done. This is the result of our 3D tracking. You can see the bounding boxes that is detecting the objects in this space. Next is like a 2D tracking results. You can see it is detecting bus, car, and the person riding, and the cars here. Yes, this is all for our application. Next, we will talk about our improvements.
To improve the performance, we propose two improvements in each of the two categories. First one is to improve performance by improving the tracking process itself. And the other is to improve performance by modifying the parameters used in the methodology. In the tracking process category, we first try to adjust the position based on the recent movement of the detected object. And we interpolate missing objects and smooth object passes. Then, for fine-tuning, we manipulated the matching metric from IOU to GIOU. And we fine-tuned some detailed parameters for gamma filter and matching. We first wanted to adjust the position of the object based on its recent movement. However, we struggled to do this in a 3D coordinate system, and for some reason, it didn't improve performance. We were running out of time, so we decided to change direction and propose a new methodology. To do this, we split the existing 2D tracking steps into two subdivided tracking steps. First one is high confidence association, the second data association, and the other is low confidence association, the third data association. Traditional tracking techniques perform tracking on all objects at once. However, this does not take into account the confidence of the object. Confidence generally expresses the degree to which the detector is confident about the object it detected. However, in general, larger objects have higher confidence and the smaller objects have lower confidence. In other words, the more confidence an object is, the more information it can utilize. As shown in right figures, we split the existing association into two parts: high confidence tracking and low confidence tracking, to allow tracking that take into account the confidence of the objects. By matching high confidence object first, we can match a large and clear object first. And by matching a low confidence object with unmatched detections, we can match unclear objects and occluded objects. This split association step allows us to match objects with more information about them, making it easier to track occlusion or small objects. Next improvement we worked on is interpolating missing passes by occlusion. We used Gaussian Smoothed Interpolation, the GSI. It is a technique used to create smooth transactions or predictions by combining interpolation methods with Gaussian smoothing. The GSI can improve tracking in three ways. First, it handles occlusions, where an object disappears temporarily from the frame. It also corrects missing detections, which objects are not detected in certain frames due to noise or limitations of detection model. Lastly, it also provides smooth trajectory predictions for objects that maintaining natural movement patterns.
Furthermore, we improved the distance metrics. Matching metrics like IOU, which is intersection over union, are critical in object tracking. They determine the similarity between predicted and ground truth bounding boxes. IOU has limitations too, particularly in handling disjoint or partially overlapping boxes. But first, to explain what is IOU. IOU measures the overlap between two bounding boxes. It is commonly used in tracking algorithms, but limited when boxes are disjoint or poorly aligned, which means that IOU value is non-zero for overlapping boxes, giving a good matching matrix. For disjoint boxes, IOU equals 0, as the boxes are not matched, even if the boxes are close. In contrary, there is a generalized IOU, which extends IOU by penalizing disjoint, poorly aligned boxes. It incorporates the smallest enclosing box to account for spatial relationships. This means that for overlapping boxes, GIOU and IOU give similar results. For non-overlapping disjoint boxes, IOU equals 0, but GIOU adds a penalty providing a better gradient for optimization. This can be seen in the image on the right side. IOU ignores spatial relationships between disjoint boxes. There is no penalty for misalignment outside the overlap region. GIOU, on the other hand, penalizes disjoint boxes with negative values and captures spatial relationships better. It improves more informative loss signal for tracking and detection tasks, as well as encourages better box alignment during matching. In addition, we tuned several parameters to increase the performance of the original eagermod code. eagermod uses different constants during the fusion, which means the Kalman filter, and the matching process down the line. Each of these parameters are fixed, but their optimal values vary depending on the model, dataset, or the improvement approaches we used, such as the matching metric. First, we modified the parameters of the Kalman filter. In autonomous driving, the vehicle itself is dynamically moving, making it susceptible to various noises. Therefore, by adjusting the initial value of the internal covariance matrix of the Kalman filter, we gave it a higher uncertainty about the detected objects. Furthermore, we changed the thresholds used during matching to lower numbers, allowing more objects to be detected and potentially matched. Unlike CCTV, which observes large crowds of people, in autonomous driving, vehicles are not densely packed. Therefore, two different objects are not so close together that the lower threshold makes it more likely that they will be matched with the same object rather than a different object. This can allow objects to be matched that would not have been matched before because they did not reach the threshold. And these are the evaluation results. We implemented our improvements on two different deep neural network models, on AB 3D MOT and Point GNN. Starting from the original eagermod code, we evaluated it using the Kitty dataset. Then we implemented the respective improvement steps individually and evaluated them separately as well. Finally, we combined them all and assess the multi-object tracking improvement. We can see that we were able to slightly improve on the base code with each approach. The combined approach improved multi-object tracking more than the approaches individually. Although we were able to make small improvements, it showed that further improvements need a paradigm shift of the basic approach. Simpler improvements, such as improving the distance metrics, as well as adding onto the pipeline by using a third matching step or an interpolation step, cannot improve the tracker significantly. Now for the conclusion, starting from the eagermod multi-object tracking system, we replicated it on our computers using both the Kitty and the NuScenes dataset and visualized the tracking. We then aimed to improve its performance using various steps. We divided the association step, respectively, added a third data association step. We added an additional step to interpolate missing paths generated through occlusion. We improved the matching metrics for intersection over union to generalized intersection over union. And we optimized the basic parameters used in eagermot. Through these approaches, focusing on the tracking part, we were able to improve the performance of the tracker. Although we were able to make improvements, it showed that further significant improvements need a paradigm shift of the basic approach. Such may be achieved by considering improving the fusion process or the detection accuracy. Thank you.